Hey, everybody. It's Wednesday, April 14th. And as you can see here in the aim today, our goal for today's video is really to answer this question. How does the electrostatic force get transmitted between two objects that are not touching? That's the main focus of today's video. And so let's take a moment before we get into that to look back at what we've previously done when it's come to static electricity. When we started the static electricity unit, we spent some time talking about like that basic middle school rule of how charges interact with each other. That opposite charges will attract and like charges will repel. And in Monday's video, we talked a little bit about how we can quantify that and how we can use some like real physics terminology to describe that. As we mentioned, since we're talking using words like attraction and repulsion, what we're really getting at in terms of physics terminology is that objects, when they are charged, exert forces on other charged particles. And what we did on Monday was we took a look at the law of physics known as Coulomb's law to quantify the force that is exerted between charged particles. But of course, we have to get at this fundamental question of how is it possible for these objects to be able to push and pull on each other without actually touching? Now, we have actually looked at a force like this before this year, but the force that we've looked at so far this year that is similar to electricity is unlike all the other forces we've talked about this year. When we talk about things like an applied force or the normal force or the friction force or like a tension force in a string, usually what we're talking about are forces exerted by objects which are in contact with one another. If you have a block sitting on a surface and that surface is exerting a normal force on the block, it's because the block is in contact with the surface. It's the same thing for the force of friction. The objects are rubbing on each other. If somebody takes their hand and pushes it into a block and applies a force on the block, they exert that force by touching the block. The electrostatic force, like gravity, is a force that can be exerted between objects that never, ever, ever touch. And whether or not you realize that, it is important to realize that these objects do exert forces on each other without ever touching. And that's a key distinction. Now, I've obviously not demonstrated this to you in the front of the classroom because we are not sitting in the classroom. So let's go take a look at objects exerting electrostatic forces on each other without touching. So here in this video, we've got our old friend Bill Nye, the science guy, and he's rubbing that balloon on his head, and then he's holding it next to this balloon. And as you can see, this balloon never gets into contact with the other balloon before it pushes on it. There, he's rubbing it on his head. And as we said, by rubbing something on your hair, you are causing your hair to give up its extra electrons. Now, Bill Nye's hair it has extra electrons which are transmitted to the balloon. And those excess electrons sitting on the balloon are now going to come up to that balloon hanging on the string. And notice it repels the balloon on the string. That's the key idea here. It's repelling the object by pushing it away. Notice here he's going to do it again and give it an additional charge and show it. And now we can skip ahead here to show him do this with some other materials. Now, notice in this segment, he's taking a rubber rod and he's rubbing like some fur on it. And so what you can notice is, like the other balloon, the rod now also repels the balloon. Now, of course, we can ask the question, well, what does that tell us? It tells us that when the fur was rubbed onto that rubber rod, like Bill Nye's hair onto the balloon, that fur gave up its extra electrons and now transferred them to the rod, and the extra electrons on that rod repel the balloon. Now notice he's going to take a glass rod and rub it on the fur. And what's important to realize is glass is just a fundamentally different material than rubber. It has a different atomic structure. There are a different number of protons and electrons. And so the way it interacts with the fur is different. And so notice when he holds the glass close to the balloon, instead of repelling the balloon, now it attracts the balloon. And the most important thing for you to realize here is that it does that without touching. The glass rod attracts the balloon without coming into contact with it. Now, of course, what that tells us is because the glass is different from the rubber, then when the rabbit fur was rubbed onto the rod, instead of giving up its electrons, it actually took electrons away from the glass. And because it took electrons away from the glass, it ended up leaving the glass with more protons than electrons. And so effectively, it gave it a positive charge. And now, instead of repelling the balloon, it attracted it. And as we can see here, it will continue to attract, all the while without contact. And so now that we've really seen this in action, we are ready to get to the heart of today's video, which is how is it possible for objects to exert forces on each other without touching? And it's important to realize that the thing we are about to talk about here is a model. It is basically an invention of scientists. Scientists say, well, how is it possible for objects to exert a force on each other without touching? And they create this idea. And that idea is known as the electric field. What scientists say is that there is a region of space around a charged particle or object like a metal sphere, and that region of space has an electric field in it. And that electric field is responsible for transmitting the forces between the two objects. Now, some of you might be listening to that and think that that's totally bizarre, that like, wait a second, the electric field is just an idea that scientists made up. Yeah, it is. That doesn't necessarily mean it doesn't exist, of course, though, even though it is just made up, because, well, that's how science works, right? This is not just some made up fantasy idea. Scientists say there is an electric field around an object, and if there was an electric field around an object, the objects would behave like this. And that is exactly how we see objects behave. So this idea was like sort of hypothesized. It was kind of just made up. But of course, our ability to do experiments and test ideas is ultimately what allows us to conclude that this is, in fact, correct. Take a second to pause this video here and write that down. And when you hit play, we'll move on. So to be clear, moving forward, there are basically two separate discussions that we are going to have as we move through this video. The first is about how we can use diagrams to describe the electric field without numbers. And then the second is going to be how we can use an equation to quantify the strength of an electric field. And so the first thing we're going to say here is how we can represent the electric field qualitatively, or in other words, without numbers. And the way we do that is with electric field diagrams. And so I'd like you to draw this under the heading Electric Field Lines Drawing Convention. This is a huge note. Electric fields are represented by diagrams with lines called electric field lines. Electric field lines are drawn to show the motion of a positive test charge. This needs some explaining. An electric field line diagram is a diagram with a charge. That charge is going to have an electric field around it, and lines with arrows. Those arrows are drawn to show you the motion of a positive test charge. And so, in other words, we imagine placing some small positively charged object around the object of interest. This is the thing we're drawing the field for. And the lines point in whichever way that positive test charge would move. Now, I'm going to show you a bunch of different examples here. I want you to keep that in mind. I'm going to bring that up over and over again. But electric field lines are drawn to show the motion of what a positive charge would do around that object. Take a second to pause this video here and write that down. And when you hit play, we'll move on. So what I want to do here now at this point is we are going to go through and just take a look at electric field line diagrams for a bunch of different situations. These are all situations you absolutely have to know and be able to identify in multiple choice questions. And so I highly recommend you draw these carefully. The first one we're going to look at is the electric field around a positive test charge. Now, the first thing we should say about the electric field line diagram for a single charge, you'll notice this when we get to the negative charge diagram as well, the electric field lines exist radially out from the charge. So they basically spread in a circle, what I mean here, in every direction. So what I'll write here is the field lines spread radially in all directions. Now, if you notice here, what we also said is that these electric field lines show you the direction of motion for a positive charge. Don't go too nuts about this. This is very straightforward. Basically, to understand which way the arrows should go involves us in answering this very basic question. If I put a positive charge here, so a positive charge right there where I drew that red dot, how is it going to interact with this positive charge? They're both positive charges, so this positive charge here represented by this red dot would be repelled. And so that's why the arrows go away from a positive charge, because wherever you put a proton or any positive charge around this main positive charge here shown in blue, it's going to move outward. It's going to be repelled by the positive charge. And that's why the electric field spreads around like this. That is a very important point. And so, like I said here, I want you to take a second to pause this video here and draw this diagram. Draw the electric field lines, represent the spacing, put them like this, and when you hit play, we'll move on to the next example. All right, now we looked at an example for the electric field of a positive charge. Now I want to show you one for a negative charge. In a totally unsurprising way, based on what we've already said so far in this video, the electric field line diagram for a negative charge looks like this. The first and most obvious question we have to ask here is, what is the difference between these two diagrams? And the only difference is that the electric field lines for the negative charge go in towards the charge. This makes a heck of a lot of sense if you think about it. If we put a positively charged object over here on the top left corner of this image here, right over here, and we said, what is this positive charge going to do in response to this big negative charge over here? It's going to be attracted. And if we put positive test charges all around this negative charge, all of those positive test charges would be attracted. And so they would go towards the negative charge. And that is why the electric field lines point in to a negative charge. Take a second to pause this video here and write that down. Sketch this diagram as it is shown. And when you hit play, we'll move on. So I think one thing that we can sort of use here to rewrite the rule is that the electric field lines are always going to look like this for a positive charge, and they're always going to look like this for a negative charge. Because while it is like the main way that physicists always phrase the rule is that the electric field lines are drawn for a positive test charge, that is true, and that is the thinking around how these diagrams work. But I think it's much easier to rephrase the rule by just saying electric field lines always come out of positive charges and they always go into negative charges. That's the same thing, just said in a slightly more understandable way. So take a second to pause this video here and write that down. And when you hit play, we'll move on. We are not only going to look at electric field line diagrams for just a positive and a negative charge, but also for a system of two charges. And so let's take a look at the electric field line diagram for opposite charges, a positive and a negative held together. Now, the first thing we should say is all of the electric field lines come out of the positive charge and go into the negative charge. That's the first point. The second point we should make is that even if the electric field lines are off of the picture, it doesn't mean they don't exist out there. This electric field line that my pen is hovering over right over here actually comes up off the screen and loops around like this. You just can't see that because it's not pictured in the diagram. The other important thing to note here is that these lines show you how a positive charge would move. Now, this is what I see in the past when I give this on a test and ask kids to explain this. They say the reason these electric field lines look like this is because the positive is attracted to the negative. That is 100% wrong. The reason why the electric field lines look like this is because they show you what a positive charge would do if we put it anywhere around these two charges. Let's say we put a positive charge here for a moment. Now, of course, this positive charge is going to be repelled by the main positive charge, and it's going to be attracted by the red negative charge. But it is closer to the positive charge. And since Coulomb's law the law that describes the forces exerted between these charged particles, says the closer together objects are, the larger the force they experience, tells us that the repulsion experienced by this test charge is going to be larger at first than the attraction it's going to feel towards the negative charge. And that's why it ends up curving around like this, because the blue charge, the blue positive charge, just does its best to push this thing away, like almost out in a straight line. But of course, as it gets closer and closer to the red negative charge, it's more and more and more and more attracted to the negative charge, and so it eventually curves over towards the negative charge. Of course, if we put a positive charge right in the middle, right here, it's going to be equally repelled by the positive charge as it is attracted by the negative charge, and so it's just going to move over there in a straight line. These lines do not show you really anything about what these charges are doing to each other. They are showing you what these charges are doing to a positive test charge. Take a second to pause this video here and write that down. And when you hit play, we'll move on. And the last example we want to look at here is the electric field for like charges. Now, notice this particular diagram is shown for two positive charges, and that's why the lines are coming out. But this is what the electric field line diagram looks like. And again, this electric field line diagram is showing you what would happen to a positive test charge. The reason why these lines curve up like this up here at the top is because if we put a positive test charge right there, it's repelled by this positive charge, but it's also repelled by this positive charge. And that's why it just comes up, out, and away from the two positive charges. The lines are always coming away from both of these positive charges because any positive test charge that we put out here is going to be repelled. Now, before I ask you to stop and pause this here, I want to take a moment just to focus on this region of space between the two charged particles, because this, I find, is often a pretty confusing part of this diagram. Generally, the question that we ask about this part of the diagram is, well, why is the diagram blank there? And it's not really because there's no electric field there, but it's because there's no net electric field there. You have to think about what a positive test charge would do. If I put a positive test charge right in between these two positive charges, it's going to be repelled by this charge here on the left and repelled by this charge here on the right. And so it's going to have a force exerted to the left by this charge on the right, and it's going to have a force exerted to the right by this charge on the left. And those forces are going to cancel each other out. And so the reason why there's blank space in between these two charges is because whatever force they would exert on a positive test charge will be canceled out by the other charge. And that means the electric field in that region of space cancels. The net electric field is zero. You would get an electric field line out of this positive charge here that goes like this, but you also have an electric field line out of this one that would go like that. And so the basic idea is they cancel. Take a second to pause this video here and draw this diagram, and when you hit play, we'll move on. All right, now just very quickly before we get into the math side of this here, there are a couple of loose ends that we want to tie up here. And the first one is, this is an electric field line diagram for like charges that both happen to be positive. What would this diagram look like if the charges were both negative? What do you think? The answer is it would look exactly the same. The only difference is that the lines would just go into the charges instead of come out of the charges. That's a very important distinction. The electric field lines always come out of positive charges, and they always go into negative charges. Take a second to pause this video here and write that down. And when you hit play, we'll move on. All right, now we've got a big question to ask here. And I think that this is really going to be important not only for this particular topic, but also when we get to magnetism. And the big question that we have to ask is, what does the spacing of the electric field lines show us? And the easiest way that we can answer this question is to just go back to the picture of an electric field line diagram for a single charge. What happens to the spacing between these two lines as you get farther away from the charge? Should be obvious to everybody. The lines are getting farther apart. The question is, what do you think that means? What do you think happens to the electric field as you get farther away from the charged particle that's producing the electric field? I think the answer is pretty intuitive. When you get farther and farther away from an electrically charged particle, the electrical field gets weaker. And so the electric field line spacing shows you the field strength. The closer the lines are together, the stronger the field is. The farther apart the lines are, the weaker the field is. And as a result, E-field lines never intersect. Now, you should take a moment to pause this video and write that down because this stuff is like super, super, super important. But we should just quickly say, notice whether it was the video where I rubbed the comb on my head and I held it close to that piece of paper, or that video that you just saw where Bill Nye took the balloon and rubbed it on his head, that you only really see the balloon get repelled by the other balloon when it gets to a certain distance away from the balloon. That's because when the balloon is really far away from that balloon on the string, the electric field is so weak that the force produced by that electric field is so weak that it barely moves the object. The point is, the electric field transmits the electrical force, and it gets weaker and weaker the farther you get away from an object. That's represented in these diagrams by the spacing of the field lines. Take a second to pause this video here and write that down. And when you hit play, we'll move on. Now, I think the coolest thing about science is that scientists can just basically make up ideas and then test them to see if they're correct. And if nature works exactly the way scientists predicted, then we have a pretty good idea that the idea they came up with was right. The concept of the electric field was entirely invented by a human being. People just said, what if there's an invisible field around the charged particle? That is how they push and pull on each other. So it's a totally weird idea. But now that we have advanced technologies, we can actually see the electric fields, or at least get a good sense of what they look like. Here, we have a charged particle here represented by this black dot. And basically, if you take a bunch of little specks of iron and you put them around the charged particle, they all line up in a very particular direction, exactly as the field was predicted. And that's pretty cool. Now, with the conclusion of this part of the video here, where we're done now looking at the electric field line diagrams, we're ready to transition to looking at the equation for the electric field strength. I think you'll find this is pretty straightforward. Write this under the heading electric field strength. The definition of electric field strength is that it is the amount of force exerted by the electric field per unit of charge, or per coulomb of charge. And so basically, if the electric field strength is 1, that tells you there's 1 Newton of force exerted for every coulomb of charge. That definition means the equation should not look like much of a mystery here. But first, we should say the symbol for the electric field strength is an uppercase E. The equation is E is equal to Fe divided by Q, the force divided by the charge, or in other words, the force per unit of charge. Fe is the electrostatic force measured in newtons, Q is the electric charge measured in coulombs, and E is the electric field strength measured in units of newtons per coulomb. Basically, the number for the electric field strength tells you how much force per coulomb of charge. And that's it. It's pretty straightforward. After all, it is the field that is responsible for the force being exerted. So if we want to quantify the strength of the field, it should be in terms of the force it is responsible for producing. And so that's why the equation looks the way it does. Take a second to pause this video here and write that down. And when you hit play, we'll move on. All right, let's take a look at a problem. This problem here says, what is the magnitude of the electric field intensity at a point where the proton experiences an electrostatic force with a magnitude of 2.30 times 10 to the negative 25 newtons? So they tell us here that the force exerted on this proton is 2.30 times 10 to the negative 25 newtons. It's a pretty tiny force. And that's the only number they give us. They ask us for the electric field strength. What are we supposed to do? We don't have all the information. There's one word in this problem that is more important than all the other ones in terms of being able to answer this, and that would be proton. It is very, very, very important for everybody to remember that the charge on a proton is equal in magnitude to the elementary charge, which has a value of 1.60 times 10 to the negative 19 coulombs. And so we can say here that the electric field strength, as given by the equation we just developed, is Fe over Q. And so plugging in our numbers here, we have E equals Fe, the electrostatic force, 2.30 times 10 to the negative 25 newtons, divided by the charge, positive 1.60 times 10 to the negative 19 coulombs. And then we do that math here. Notice here, because we're dividing, we have to subtract the exponents in scientific notation. And so we get 1.44 times 10 to the negative 6 newtons per coulomb, which is choice 2. Take a second to pause that video here and write that down. And when you hit play, we'll move on. So, of course, we should ask a basic question here. And that question is, well, what does that number actually mean? We can determine what that number means based on the definition of electric field strength. The electric field strength, as we said, is defined as the amount of force exerted by the field per unit of charge. So that tells us the magnitude of the field strength, tells us the amount of force exerted on each coulomb of charge is 1.44 times 10 to the negative 6 newtons. Take a second to pause this video here and write that down. And when you hit play, we'll move on. But now, of course, that we've answered that question, we've got another question to ask. If each coulomb of charge experiences a force of 1.44 times 10 to the negative 6 newtons, then why does the problem say the proton only experiences a force of 2.30 times 10 to the negative 25 newtons? I actually want you to really think about that for a second. Take a minute to pause this video and think about that. If the answer to the question says each coulomb of charge gets 1.44 times 10 to the negative 6 newtons, then why does the proton only experience a force of 2.30 times 10 to the negative 25 newtons? The answer here is pretty straightforward. Each coulomb of charge experiences a force of 1.44 times 10 to the negative 6 newtons. A proton, though, is not a whole coulomb's worth of charge. It's 1.60 times 10 to the negative 19 coulombs. And so it experiences a smaller force. That's the key idea. A coulomb will experience 1.44 times 10 to the negative 6 newtons of charge. A proton is not a coulomb. It's not even close. Take a second to pause this video here and write that down. And when you hit play, we'll move on to the last thing for today. All right, this comes up from time to time, so I figure we might as well talk about it because it will take us about 2 seconds. We might as well take a moment to talk about what the equation looks like for the electric field around a single charge. And we can say here that, in general, the electric field strength is given by the equation E equals Fe over Q. But as we said in Monday's video, the electrical force is given by the equation K Q1 Q2 over R squared. And so it's important to realize what we can do here is we can basically substitute that equation in to the electric field equation for Fe and see what we get. So notice we're basically just replacing Fe in this equation with K Q1 Q2 over R squared. Now what you'll notice is one of these charges will cancel. And so what we're left over with is K times Q, and there's no reason to call it Q1 anymore because, well, it's just one charge. And then we're going to divide that by R squared. And what this equation says is that if we have a single charge sitting in space, the size of the electric field around that charge is determined by this equation. That tells you if the charge is bigger, the electric field is stronger. That makes sense. And it tells you if the distance between you and the charge is bigger, the electric field is weaker. Take a second to pause this video here and write that down. And when you hit play, we'll wrap it up for today. Now, of course, the most common question asked about these relationships with the electric field strength and the charge and the electric field strength and the distance is, well, if we were to draw a graph of the electric field strength versus the distance, what would it look like? And you've now had enough experience with this to be able to say that when two variables are inversely proportional, they should look like this on a graph. And that's really it. And with that, that's actually it for our main discussion of electric field strength. Have a good one, everybody.